Professor Parthapratim Munshi. Munshi received his PhD in 2005 under the supervision of Professor Guru Rao from the Indian Institute of Science at Bangalore. Next, he carried out his postdoctoral research in the group of Mark Spackman at the University of Western Australia at Perth. In 2008, Munshi was awarded the prestigious Marie Curie International Incoming Fellowship to work with Dr. Christian Jelsch as a postdoc at the University of Nancy in France. And at that time, Munshi came to Warsaw for some time, and we still remember his visit. In 2008, Munshi was, after 2 years, he moved to the USA to work as a research scientist at the Oak Ridge National Laboratory, where he was associated with Tibor Korytsański and Professor Flora Meile. Professor Munshi joined Shiv Nadar University in 2013 as an assistant professor. In 2018, he was promoted to associate professor and assumed and become, as I understand, the head of the department. In 2021, he was promoted to full professorship.
Partha has a very strong research interest in multifunctional organic materials, polymorphism, biological active compounds, protein-ligand interactions, medicinal chemistry, molecular docking, molecular modeling, also high-resolution X-ray crystallography and quantum crystallography. He authored over 70 scientific research papers in peer-reviewed international journals. In 2019, he was named the Emerging Investigator in Excellent Award by Shiv Nadar in 2021. Currently, he's a member of University of California, Berkeley's Executive Leadership Academy alumni. Recently, he has been appointed as a member of the editorial board of Cris&Com and Journal of Molecular Structure. Currently, he is a member of the National Committee for the International Union of Crystallography and Commission of Quantum Crystallography of ISUL. He is a fellow of the Royal Society of Chemistry, London, UK. Professor Munshi will talk on the potency of polymorphic bioactive molecules, a quantum crystallographic perspective. Partha, the screen is yours.
Okay. Thank you, Professor Krzysztof Wozniak and Professor Paulina Dominiak. And just to confirm, am I audible clearly? Yes, great. So yeah, thank you very much for your kind introduction. And I feel it's my actually honor to be part of this series of distinguished lecture. And again, I'm thankful to both of you for inviting me to present our recent research work. So today, I'll be talking about mainly on the potency of polymorphic bioactive molecules. And I'll give the quantum crystallographic viewpoint. So to start with this lecture, keeping in mind the broad audience, although I do not need to introduce what is polymorphism. However, for the continuity of this talk, I'll be starting with the very basics of polymorphism and in very brief. And then I'll be talking about the drug polymorphism and what is the current status of it. To some extent, I'll cover that. And what are the different approaches to improve their potency? And if any new approach can be introduced, and whether quantum crystallography can help us understanding the variation of the potency of this polymorphic drugs. Well, so as I said, to start with, let me introduce. Of course, there are several definitions of polymorphism, but this is the definition which still stands out, and it's very much valid. Well, I'm introducing these terms, the different type of polymorphism, because I'll be using these terms in my lecture. So the first one is conformational polymorphs, as it sounds like, the conformational differences. And if I take the, let me take the pointer here. So this is kind of, if the molecule is having flexibility, then they tend to have differences in conformation, and they may give rise to conformational polymorph. It could be, interconvertible or may not be. The other one could be packing. That is nothing but the different packing arrangement of the same molecule. Concomitant, when at least two different forms crystallize together, as the term suggests, concomitant. The other one is a bit puzzling one, isostructural, which is a bit of contradictory term, that different but similar, means same molecule, different crystal structure, but there is a similarity in the crystal structure. For example, apparently this looks very similar, but they are different. Well, if we look from the thermodynamical point of view, then that could be monotropic or enantiotropic. Well, everything is included in this book. So now, this is the brief about the polymorphism in general. There are a lot to talk about it. However, focusing on today's topic, I'll be now talking about the polymorphism in bioactive molecules. Well, what is the importance of this polymorphs in case of, say, the drugs? There are several articles, reviews. However, few of them I have just highlighted over here. And as the title suggests, the importance on the drug development process and the importance of the polymorphism. And what are the phenomena that affects their performance? That's why the potency variation, whether we can tune them. Well, this book is a very good source of such studies specific to pharmaceutical solids and their polymorphic behavior. But this are the two codes which essentially tells that how the different forms can behave as far as the drug molecules are concerned. As it says, the particular polymorph can be responsible for a particular property, means they're specific, which might not be exhibited by any other form. It might be completely different, or it says also polymorphic forms of a drug differ in physicochemical properties like dissolution, solubility, chemical and physical stability, flowability, hygroscopicity. So these are the sum of the physicochemical properties. However, we'll see beyond this what we can think of and how it can affect the drug development process if we somehow overlook this polymorphism. Well, I have listed few of such drugs which are known to exist as polymorphs. Here I have listed about 34. I'm sure this is not the exhaustive list. There could be a few more. However, just to give some idea that this is not uncommon to have polymorphism or polymorphic forms of drug molecules. Well, among all these, I'll be just picking one of them. That's ritonavir. Most likely, the next speaker, Dr. Marcos, would be talking more about it. However, here, I'll be highlighting this to let you know, or to basically convey the importance of polymorphic study in case of drug molecules and what all disaster it can create if we overlook them. So when it comes to ritonavir, in the market it is known as the Norvir in the form of capsule, and this was discovered in the year of 1996 at this laboratory, Abbott laboratory at Illinois. Well, this is used for treating the HIV infection. Soon after that, means after 2 years, it turned out that this particular drug exists in polymorphic form. And the second form actually turned out to be more stable, and it is about 50% less soluble. So that from the dissolution study, it failed. And that actually compromised the oral bioavailability. No wonder this particular drug had to be forcefully removed from the market. Well, the particular study was reported in 2001 in this journal, and where they have reported this stable form 2, which exists in the trans form, and that is actually having this kind of solubility difference compared to the cis one, which is the original form and which was available in the market. Well, soon after, means after 4 years, there are discovery of 3 more new forms, and one of them is the metastable polymorph. These others 2 are either hydrated form or the solvated form. However, the crystal structure of this particular metastable form was not reported because of the tiny crystal they could know. In other cases, anyway, these are the hydrated or the solvated forms. So overall, there are 5 forms so far known for this particular drug called Norvir or the ritonavir. Well, so as I said that, this is a major concern that we need to, of course, look for it and do the thorough screening of drug molecule for that. But there have been a lot of efforts actually for improvement of the physicochemical properties. Few of them I have already mentioned in my previous slides. So, and specifically for the API, co-crystallization, that has been a very common approach, but there are some challenges that one need to identify the safe co-formats and also predict their performance during dissolution or the solubility experiments. So there one has to very, select the coformer carefully. However, there have been some success with the drug-drug co-crystallization to get rid of that coformer challenge part. But what we have realized is that the polymorphic modification, the approach, could also be useful, but it has been explored to the very least. Well, what is reported so far through the polymorphic modification, whether the potency of the bioactive molecules, I'm not talking in general the physicochemical properties, but other properties, in solution properties, or the bioactivity, whether that can be improved by a polymorphic modification. Because we know the polymorphs, as mentioned a few minutes before, that each and every form can behave completely differently. So some of the form could be even much more active compared to the known one or the other one. What is known so far? So from the literature, what we see, there is one report in which, for this particular drug, they have looked into the anti-inflammatory activity. And there are 3 forms whose crystal structure are also reported. These are the rep code from the CCDC in the bracket for your convenience. So 2 of them are very identical conformation wise. In other cases, there are 2 molecules in the asymmetric unit. However, what they reported, the anti-inflammatory activities are varying in this. The form A has much higher activity or higher activity than the B, whereas form C, it does not show any activity. So that's the the difference in properties we are talking about. I'm not going into the detail of it. There is another report in 2018 for this particular drug. There are 2 forms they have reported, monoclinic and the orthorhombic form. In this case also, the conformationally they are not so different, this much RMSD. However, when they look into when they studied the pharmacological tests, then what they have found for the analgesic or the anti-inflammatory activity studies, that monoclinic form is much more active than the orthorhombic form. And what they have discussed in this paper, that this type of variation or the variation in the activity is essentially due to their structural variation. Whereas the monoclinic form, actually it forms chain-like structure. In contrast, the orthorhombic form, between the two layers, there is a dimer. So as per this discussion, the breaking the dimer could cause the low activity compared to the monoclinic form. Well, so to our knowledge, these are the two so far reported as far as the bioactivity is concerned. While the first report also complemented the study with docking studies only, however, they found the binding energies very close to each other. Well, so what we have done in this recent study, we have considered this 5 compounds of this moiety, and in our earlier study, this is a collaborative study, there it was actually characterized as they are known to show the anti-tumor activity as well as the anti-mitotic activities against the breast cancer cell. In this process, it has also been identified the human gamma amylase as enzyme as the target for this type of molecules, the bioactive molecules. So here we have considered 5 of them with certain substitutions in these groups, and these are our contributors, then my PhD students, my collaborators, and together we have put a case study concerning this particular, the series of compounds over here. So what we have done, Anil actually did the excellent job to the crystallization, and in the crystallization process, our actually aim was to find the polymorphism in this case, and we could discover actually 8 polymorphs in the first 3, 1, 2, 3, for the first 3 compounds. And this is the the different ways we could get the different forms, be it simple solvent evaporation method or via melt crystallization, and so on. So one case we had 3 forms, another case also we have 3 forms, and in the third case we had 2 forms. And as you can see, when you looked into the structural overlay, then that appeared to show this type of differences or the similarity. When it's a similarity, well, then we had a look at the RMSD, that's from the crystal geometry, and what we find, form A, 1A and form 1B is kind of this, whereas the other case is much more the deviation. So these values, what it suggests, okay, there is some guidelines. These values, these 2 cases, we have the values of RMSD less than 0.375. So the question was coming in mind whether to call these as the, whether these are conformational polymorphs or not. Well, so from this particular review, as it discussed, the decision tree to identify whether the 2 polymorphs are conformationally related or not. Well, there are certain criteria. In this, the third one, in our case, the third one suggests that, okay, we have looked at from the structural point of view only. And then what we find that, yes, some of them are conformationally related between 2A and 2B, but not 2A and 2C. Similarly, not 1A and 1B, but 1A and 1C and 1B and 1C there, and so on. Whereas 3A and 3B, yes, there. So that's how we're confirming that some of them are conformational polymorphs. Well, what else we have done? When we looked into the energy framework analysis, and then through this also we have got the interaction energies, and then also we calculated the lattice energies, and to basically find out that which form is more stable than the other also. So this is sort of, these are the values which indicates that one is more stable than 1B, than 1C in this case, and so on. Well, so these are the, based on the crystal structures, coordinates, all this analysis. Further, for compound 4 and 5, we did not get any polymorphs. However, when you looked into their energy frameworks, then what we realized that form 3 had 2 polymorphs. Out of those 2, one of them are having isostructurality, although 2-dimensionally, as you can see that in which two direction the similarity is coming with respect to the 4 and 5. And they are actually 3-dimensionally isostructural. Means all the 3 directions, their apparent packing or the energy frameworks looks very similar. And these are the sort of values which tells us the degree or degree of the similarity or the dissimilarities. So now, why we are talking about this isostructurality? So 3 had 2 polymorphs. Now 3b is isostructural with this. Now, if we think of the structure property relationships, then in that case, if 3b, one of the polymorphs are active, then 4 and 5 also we believe that could go in the, or many of the properties could be similar. Well, we'll see what we got. Further, other than those, the solid state properties, of course, we have done the thermal stability, etc., all sorts of solid state characterizations. Then we have chosen the first 3, means the polymorphs of compound 1, and we have looked into their equilibrium solubility as well as the intrinsic dissolution rate. Well, in 2 media, and what we have noticed, their equilibrium solubility are varying in this fashion. In this order, 1A solubility is least compared to the 1B and 1C. So 1 is most stable. Of course, energetically we have noticed that. So there is correlation. Similar trend, we got it for the IDF profile, and this is what it looks, and the order is in this. So these 2 are, yes, definitely correlating. So what we noticed between these 2 media, in case of acidic media, it is having, so the solubility is better or the dissolution rate is faster. What it means that this particular drugs are more active in case of highly acidic condition. Well, at this stage, we also thought that, okay, for doing this calculation, what we had to do, we had to select the individual polymorphs, then mechanically grind them, make the pellet, do this study, that means dissolve them, and then we were curious to know whether they are interconverting or if there is any changes in phase. So the phase stability analysis was done with the powdered XRD before doing that experiment and after doing that experiment. While this pattern clearly shows that there are no changes, which basically telling us that they do not interconvert. Well, what we are showing here, the final effect means before doing the experiment and after doing the experiment, means after drying the solution, then from that we did the powdered XRD, and this is what it is indicating. So this at least confirms that even after grinding and this dissolution, it does not change or convert to another form. However, still, it is not clear that what happens when it is in solution. General concept is that given this type of molecules, these are not kind of extreme conformational polymorphs, or 1A, 1B is not anyway, but 1A with 1C and 1B with 1C, they are conformational. There are some significant changes. The question arises that, in fact, this is how the review helped. In one of the reviewers actually asked this question, whether what happens in their solution, whether if we can do the enema and see. And what we did, we dissolved the individual polymorphic forms in DMSO, because rest of the bioactivity study, which I'll talk about it, we have done in DMSO. And from the apparent look, when we do stacking from the stacking pattern, they look all identical. However, when we zoom them, then what we see, you remember that we had this type of conformational difference. So the major difference was coming in this benzene ring or this amine group. So when you looked into the chemical shift, of course, we have to match the DMSO peak first and then see the differences in the if there is any shift in the peak positions, and we do see indeed there are, of course, given 1A, 1B, there's such a similarity, still there is some changes, whereas for 1C, it was significant. So that says that the conformation of these polymorphic forms are well maintained in the solution to some extent, I would say, because we do not really expect here the drastic changes given this conformation. I mean, such a similar, I mean, yeah, small differences. And that possibly it says that there is no interconversion is happening between the different conformations on the between the different forms. So that tells us, well, then in solution also, then they might be retaining their properties. Well, so that triggered us to look into their binding assays. Of course, as I said, the bulk forms earlier in our earlier report, the activity was measured and all, and they turned out to be active. However, through this polymorphic modification, we got the different polymorphs, different forms, and then we have done these activity studies against the MCF7 breast cancer cell, and we found this type of variation in the IC50 value. Similarly for others. Well, there are a lot of numbers. However, when I'm talking about this IC50, then as what we can see here, in general, the specific polymorphic forms like 1A or 3B, if you look at it, are more potent than their corresponding bulk form. That means through the phase separation, we could improve their activity. Well, when you look into that, the percentage binding, because gamma enolase was the target, and when we studied this, then we see that yes, they correlate well. Again, this is the highest compared to others. Of course, 1C is the most poor, and you can see here the activity as well. Similarly, between the 3A and 3B, this type of variation and this type of variation in the binding. Well, although these activities are in the range of micromolar, but this is a case study to show that yes, it is happening. It does happen in some cases. There is not only one case, but few cases. So that was sort of the, from the binding assays, we could confirm that in solution and their activities. Of course, there could be many reasons for this activity variation, the diffusion through the cell membrane and many other. But yeah, given the limitation, what we have thought at this stage now, and looking at this percentage binding to the gamma enolase, what we have done at this stage, we have done the MD simulation that was done by my collaborator, Dr. Satish Dube, whereas the previous one was done by my other collaborator, Professor Shen, and a student. And of course, when we looked into the binding energies of the after the MD simulation, then what do we see? Of course, that was against this human gamma enolase, whether there is this is the PDB ID of this apo protein or apo enzyme structure. There is no ligand bound structure reported for the gamma enolase. So what we did, we have taken this polymorphic ligands and did the MD simulation. Then what do you see? The variation. Of course, this energy variation is again correlating with the observation we made from the experimental binding assays. Similarly, for the 2A and 2B and 2C, okay, 2C is having the highest, although 2A and 2C comparable, I would say. 1A, 1B, you can see the changes. 3B. Now, 3B was isostructural to 4. That's why we did not do for 5, because 4 and 5 are the 3D-dimensionally isostructural, so they're supposed to give the similar. So anyway, when you looked into the 4 and 3B, you see that structure property holds. They're having the similar percentage, I mean, the similar binding energies. Well, these are the interaction pictures. And what you see from here, 1A, this is this. And the 2C, if you look at here, and the 3B, and these are the conventional, having the conventional hydrogen bonds, although in this case, but okay, this shows that overall, between 1A and 1BC, the drastic changes. This is having really very weak interactions, or very least interaction it's having with the active site residues. Well, just to highlight that how well this 1A, 2C, and 3B are buried inside the protein active site. This the poses are clearly shown here that they're well inside the active site. Well, then we looked into that. What happens, before and after their conformation, the RMSD, how much it is varying. So what you see, yes, the variation for 1A and 1B are not much, whereas the 2A and 2B, 2A and 2C is about 1. 2B is much comparatively higher. Between 3B and 4, yes, they are in the higher side. Well, so overall, what it says that structural conformation of the ligands that undergo not much changes. Basically, if we look at the 2 angstrom, that's too much. However, there are some changes, but not really drastic change. But if I remind you that we have looked at earlier based on the crystal structure, so what it says that similar structures, because the RMSD was less, they are undergoing minimal changes. 2A and 2C also at the RMSD in the crystal structure minimum, and there before and after also they're not changing very much. Well, so what is the take home from this first level of study, from this case study? That yes, polymorphs with distinct solid-state properties, they also exhibit significantly different not only solid-state but the in solution like solubility, IDR, cellular assays study. And also from the in silico studies, we could show that the binding energies and the conformations could be different. Well, we have shown that the sum of the polymorphic forms in some cases are much better than their bulk forms. Bulk form is supposed to be, you might have noticed that it's the average of the individual forms. The bulk form activity was indicating that. So, and okay, so we believe that in this we have demonstrated that potency of bioactive molecule can be improved by polymorphic modifications. And we also believe that it is necessary for efficient screening of polymorphic drugs and for avoiding any more human health disaster like the case of Ritunovich. Well, now the question came in your mind that what could be the reason for such activity variation? We could show that the binding energies, etc. So some complementary approaches together, it is showing the similar story. Then at this stage, we started thinking that how quantum crystallography can help, or basically the high resolution study or the multiple modeling, the charge density through this. Can we get to know more about this? Basically, it is something to do with the electronic distribution or not. Well, so that to understand that part, of course, this is the case of the molecular recognition. So what happens in molecular recognition? Of course, I do not need to go into the details. Just to give some brief idea about it, it's about the association of the small molecule and the enzyme. So that's sort of drug receptor interactions. Well, there are quite a few studies starting from 1996, and there are many more. But as the title suggests, that how this molecular recognition process actually helps in designing new drugs. That means the role of the small molecules in their drug receptor interactions. But yes, these studies, not only these studies, there are few other studies which actually tells that what happens to the pre-binding state and the post-binding. So that's very important to study, because that tells us that what are the changes it might happen, or whether the small molecule the database can be utilized for such development, drug design development or not. Well, there are some more nice studies by our colleagues Simon, or the Florian and Dylan, etc., and also Professor Wozniak and all. So what has been discussed here, as the title suggests, the similarities and differences between crystal and enzyme environment, means in the crystal lattice and they are part of the enzyme environment, how the electron densities could vary and or they are going to be similar. So from the charge density point of view, also this has been looked at in this very study. Of course, one of the polymorphs, this is also polymorphic, but in case of monoclinic polymorphs only, this interaction studies are reported. Well, in all these cases, the take home was that molecular conformation of ligands in the crystalline environment that correlates well with that of the target bound state. So what it says then, yes, they do not undergo a huge change. So they correlate pretty well. Well, that was the triggering part. I mean, basically, that is the part, I mean, the statement or the observation which was actually bothering us. And then we thought that, okay, what do we know? That molecular recognition process, in that the actually functions of the biological systems that are governed by this process. Well, now we have learned this. The molecular conformation that plays some role. And it says that pre-binding and the post-binding, not much differences. So now for a drug, if it is having the polymorphic form, then they can have the distinct modes of action. And that can lead to, different outcome of the biological functions. Well, so we thought that's the thing we need to, look into it from advanced studies. So we thought of, applying the multiple modeling based experimental electron density, or apply the high resolution crystallography concept. And this is not new, of course. Our friend Vega and Sharif have already talked about the contribution of the charge densities, and the two other references which I've referred in the previous slide, which all tells that how charge density can, what role the charge density can play in this world of medicinal chemistry or the drug development process. But in all the cases, the answer was that not only multiple modeling or the high resolution study can help to get to know, probably the electrostatic potential part maps are the most useful. But the message was that it needs to be combined with the quantum chemistry approach. So both together, which is the basis of the quantum crystallography. So here, what we have done, we have considered the cases of polymorph 1, that is 1A, 1B, and 1C, and then we try to examine the electronic factors that direct these interactions at the active site of the gamma annulus, and to start basically to find out that what is the factor, which electronic factors basically leading to the diverse binding affinities of these polymorphic drugs. Well, to show quickly that from the multiple modeling point of view, how this 1A, 1B, 1C, the electronic distribution looks, and this shows that accuracy of the model, etc. However, when you looked into the the bond paths and the bond critical points, the electron densities analysis within the molecule, means the covalent bond as well as the intramolecular, then what you notice that net electron densities for 1A and 1B and 1C is varying this way, which says that 1A has the least, whereas the 1B has the more, and 1C has the maximum. Well, that is from the covalent and the intermolecular interactions point of view. Further, we looked into the intermolecular region, and then when you look into that, then we see this type of variation. Well, what it shows, the total electron density in the intermolecular region for 1A is highest, means the 1A is actually the most of the electron densities are, compared to 1B, it's pulled towards the intermolecular region, and 1C has the least. That means 1C is the very rich in electron density compared to 1B, and 1A is the least. Well, when you looked into the the major intermolecular interactions and calculated their total energy densities, then this is the variation. So, but overall, it says that 1A, 1B goes neck to neck. Similarity is there, but 1C is distinct, and that says that earlier also that from the binding studies that 1C never bound to the system, but whereas 1A, 1B binding to the target. The question was arising that why this type of variation, and when you looked into the electrostatic potential, that was the most informative maps, which basically helped us to understand that what could be the reason. Well, we see that for 1A, there is well-balanced electropositive and the electronegative regions. That's the bipolar type of distribution, and very likely that will fit very nicely into the active site with the other residues in the vicinity. Whereas 1B has predominantly large electronegative surfaces, whereas 1C has predominantly the electropositive surfaces. So probably that's the reason which basically leading to such variation in their binding energies. However, as I said, that only this did not help us understanding completely. So at this stage, we have done the pre-binding and the post-binding state analysis. And what is pre-binding and the post-binding? This is what it is, and this is the constant optimal geometry. But what we noticed that when you looked into for 1A and 1B, because 1C never bound to the enzyme, so we're focusing on 1A and 1B, and also this type of variation was happening in their the conformational variation. So that's not much, but yeah, moderate. Whereas when you looked into the average values of electron densities for different type of bonds and all, then what we noticed that for 1B, it is consistently higher, whether it is pre-binding or the post-binding, than the 1A. That means 1B is having reach in electron densities. While we have also done brother Bishwajit, my student, who has come up with this idea, and he looked into this FMO as well as the conceptual DFT parameter to understand their reactivity. And the different parameters suggest that again 1B is kinetically more stable and chemically less reactive than form 1A. 1B is also having lower chi value, which is basically indicating that less polarizable. So this is the comparative study. What we from there, the take home is that why 1C was never binding. Most likely, this is the reason that it has negligible binding affinity to the enzyme because of this kind of reactivity. Well, with the interest of time, let me move on. And then here, what we looked at the complex form and how this ligand is actually bound to the polymorph, at the active site. So when you looked into this, the active site, and then we can see that the complementarity of the electrostatic basically surfaces between the ligand and the protein. Well, this type of variation, and what do you see? The 1B is hanging from this one side, whereas this is actually very much buried inside. Well, further, we looked into the and visualized the enzyme ligand interactions from the NCI and the RDG point of view, and that is absolutely clear from here that how much more interactions it is having and how well it is fit into this compared to the 1B. Well, this clearly indicates that within this region, that this is having the the high density peak. That means the higher binding affinity compared to the 1B, which is having the lower binding affinity. When you look into that binding energy, then we see that 1A is having 13 times higher than the ligand 1B. Well, so through this study, then what we have concluded that, well, of course, from the electron density analysis, we could see the similarities as well as the differences, but the ESP map actually gave much more information. Only electron density analysis did not help completely. Then we have also employed the theoretical approaches to get more information about this electrostatic complementarity as well as the the electron reach and the deficiency. So the electronic features of these polymorphic ligands are correlated with the binding affinities as well, and we believe that in this quantum crystallographic approach actually helped us understanding the electronic factors that diversify these binding affinities. So this, we believe that it would alleviate the drug development process. Of course, we need to do much more. So with this, it's my pleasure to acknowledge our university, that is Shivnada University, my department of chemistry, of course the India government funding agency, and our collaborators and the students. And this is my group. There are a few more who are missing, but yeah, bunch of students. And thank you very much to all of you.
Thank you very much, Partha, for this excellent lecture, which is now open for questions and comments.
Yes, we have a question from Hans Bert. Slide number 13. do you have a credible estimate of the barriers between the two solution conformations in the gas phase and in solvents of different dielectric constants?
Right, we have not studied that. The dielectric constant you are talking about. So we have not studied that yet. Yes. So probably it's worth studying it, but yeah, we have not looked at it yet.
And question from Marcus Newman.
Mm-hmm.
Do I understand correctly that you claim that solutes, some same chemical species obtained from the solution of conformational polymorphs, maintain different conformations in solution?
Yeah. Yes. So that was a bit of striking for us. Yes. Of course, if it is kind of cis and trans, then yes, they do. That is not new. But in such cases, when you looked into the enema, as I said, that individual polymorphs we dissolved. And then we performed the enema and we had the same concentration for each case. And at the room temperature in presence of DMS, so then you see this type. Of course, when we are emphasizing that difference. This is 1A and 1B is very close to each other. Whereas the 1C, we can see that large shift, comparatively large shift. So yes, this is what it is indicating, that in solution also they retain up to some extent. Of course, we do not expect that huge change will be there even in solution. Although it's think that all general thinking is that all the coformer will come to the same, means they'll be interconverting, but looks like not. And that's why probably also, this type of variation is happening for different polymorphs when you looked into the activities as well as the, binding energies, etc. So yes, that was a bit of eye-opening for us also. But as I said, that yeah, we looked into it.
And question from Uli Englert. Firstly, he says, thank you for the talk. And then, did you perform any seeding experiments?
Yeah, good point, good questions. And yes, we are curious actually, that seeding experiments. We did so. And yes, in one case it was successful, but not for all the polymorphs. But yes, we did seeding experiments for some of them. Yes, I anticipated. Yes, Paulina, I could see Hans Wittberg's questions, and I anticipated such question from Hans Witt anyway. And yes, Hans Witt, what we did, we have say 1C having the drastic change. In fact, I have not shown the comparison of temperature. What we did for the 1C polymorph, we have dissolved in DMSO again, and we started from the minus 25, and then every 10 degree we slowly increase the temperature to come back to the room temperature, and we could show, maybe I can pull it, but we could see actually that it is shifting, that because in the very low temperature to the room temperature, there is a gradual shift of the peak. And yes, we did this NMR study as a function of temperature for one of the polymorphs, which was the distinct one, that is the 1C. And that was also a piece of information, but I did not included here.
And some general question from Guru Rao. Have you understood why polymorphism at all?
It's a tricky question. Yes, yes, it's a tricky question certainly. But why polymorphism at all? But I think it's a debatable, and a lot of discussion has happened earlier too. That we need to look for it. It started as a serendipity, but not now. And when it comes to this type of drugs and all, so after this ritonavir, of course, one has to be very, very. Now, why polymorphism? I think I answered. In case of drug, I am not sure that what is intended, Professor Gaurav, what you intended in this question, from which point of view, why studying polymorphism in drugs? I think that answer I have given. Or why the polymorphism in particular these compounds? Well, the flexibility is one thing. And yes, I don't know whether I could answer to the satisfactory to you, because I'm not sure from which angle you're asking this question.
So he's now writing, we look at what and how, but have not looked at why. Okay, so the question is why?
Why polymorphism?
Yes.
Why it happens?
Probably I should have attended Professor Gura's lecture yesterday. He gave some lecture at ICDD, I think. So I think it's the punishment for me that I did not attend that. So he's asking this question. But anyway, we'll discuss this in a different occasion. But I think there is another question also.
Yeah, from Marcus Newman. What's the difference between 1A, 1B, 1?
Yeah, so I don't know whether my slides are still visible to you, Marcus. I'm just trying to go to the particular slide. So that's the difference. You can see that 1A, 1B, and 1C. So,
but maybe he wants to have explanation what bulk means. It's like
okay, bulk is actually the is the compound immediately after synthesis, means it's before crystallization. So the powder form before crystallization. That's all we mean. Sorry,
so
I should have been. Yeah.
So
I
that
should
was
have been
probably
clear.
a mixture of different.
Yeah, that's what we believe, that the before crystallization, the powder form, it will have all the forms together. So that's why if you look at carefully, if we average the IC50 values of 1A, 1B, and 1C, you'll see that we are coming close to that 6.85, the average one. But not always true. But in this case, actually, it is. So yeah.
Do we have more comments, more questions? As I do not see any. Jarosław Koniacki is typing now, so let's wait a moment.
Yeah, in any case, I'll be following these questions and I'll be answering when the next lecture is going on if there are more questions. Okay.
Can we use thermodynamically unstable polymorphs? Can we check polymorphic purity?
Well, if you can capture, then yes. Means I think I have shown some of the reports, and also in our case, that if it is, well, the question is that if it is thermodynamically unstable, that's where the challenge comes. But yes, if we can capture that form, then certainly we can do this purity check. But yes, for unstable one, the other challenges will be there.
Okay, thank you very much. As I do not see more comments, more questions, so thanks a lot, Partha, for this excellent lecture and discussion.